Good morning, friends. Today we will discuss some important predictions and success of shell model. So first, the spin and parity of a nucleus. So by the shell model or by the essence of the shell model, the nuclear properties are determined by the single unpaired nucleon, just like the atomic case. For even nucleus, the spin will be 0, always 0, and parity will be always positive. For even odd or odd even nucleus means even odd means even number of protons and odd number of neutrons. Odd even means odd number of protons and even number of neutrons. In both cases, the spin will be the angular momentum of the finally filled unpaired odd nucleon. Means the odd nucleon itself, the last odd nucleon itself. And the parity in that case will be minus 1 to the power L, where this L is that the orbital angular momentum, orbital quantum number corresponding to that finally filled unpaired odd nucleon, means where L is equal to 0 for S orbital and 1 for P and 2 for D and like that. Okay, for odd nucleus means when the neutron number and proton number both are odd, in that case the spin will be the Jp plus Jn, means the sum of the vector sum of the proton momentum plus the neutron momentum, so that their magnitude can be in between Jp minus J into Jp plus Jn. So these are the possibilities, and the parity will be minus 1 raised to Ln plus Lp, where this Ln is the orbital angular momentum of the finally the odd neutron, the finally filled odd neutron, and Lp is the orbital angular momentum corresponding to the finally filled odd proton. Okay, so we will see two examples. So first one, this oxygen 15. So in the case of oxygen 15, we can see that the proton number is 8, so the neutron number is 7. So the protons are filled like this: 1s1 by 2, 1p3 by 2, 1p1 by 2. So so the 2, then 6. So this is now 8. So this 1p1 by 2 is completely filled. So this is completely filled structure. Now for the case of neutron, there are 7 neutrons. So this 1s1 by 2 contains 2 number of neutrons, then 1p3 by 2 can accommodate the 4 number of neutrons. So now remains there only 1 neutron. So the last neutron is filled in this 1p1 by 2 shell. So that so this one is the odd unpaired finally filled neutron. So this determines the property of this nucleus. So for the case of oxygen 15, the angular momentum or the spin will be 1 by 2, since this 1p1 by 2 is the finally filled odd nucleon, and its parity will be minus 1 to the power p corresponds to 1, so the minus power 1 to the power 1, that is minus 1, so the parity will be negative. So the angular momentum will be 1 by 2, the spin will be 1 by 2, and parity will be negative, and this is experimentally verified. And for the case of oxygen 17, it is the protons is just like the oxygen 15, but the neutron configuration is like this: 1p1 1s1 by 2, then 1p3 by 2 accommodate 4 number, and 1p1 by 2 again the 2 numbers, 2 neutrons, and there remains again 1 neutron. So that 1 neutron goes to 1d5 by 2. So this is the finally filled state. So the spin is 5 by 2, and its parity will be minus 1 to the power d corresponds to the 2, so the minus 1 to the power 2 means plus, so the parity will be positive. So the spin is 5 by 2 and parity is positive, and this is again experimentally verified. So for most of the nuclei, this parity and spin can be predicted using this method. So this is the one of the great success of this shell model. So the third prediction is the magnetic dipole moments of the nucleus. So the magnetic moments are computed from the expectation value of the magnetic moment operator in terms of the nuclear magneton mu n. This magnetic moment is given by mu n into GL LZ plus GS SZ divided by H cross, where these G's, GL and GS are the G factors, and this LZ and SZ are the this orbital angular momentum and the spin angular momentum respectively. When Js equal Jz is equal to Jh cross, so this is the small j or unbolted j. The bold letter represents the vector values, but we cannot evaluate using this mu is equal to this equation, since this Lz and Sz do not have precisely defined values. Means since it is varying, this Sz and Sz means this one, and this Lz varies instantaneously and continually, but the total angular momentum J precesses about this z-axis. This precesses about the z-axis, keeping this Jz component as a constant. This Jz component a constant. Even though this Lz depends on this Lz means the z component of this orbital angular momentum L. So this varies. When this L is at here, this will be this Lz component will be this one to this one. Similarly, this S also varies. But even though this Lz and Sz varies instantaneously, this Jz remains constant. So since this Sz and Lz varies instantaneously, we cannot calculate this mu, the magnetic moment, using this equation. So we have to use another equation. So here, this equation in this equation we substitute this this Sz this Lz is replaced by using this equation, means Lz is given as Lz is equal to this J minus Sz, means using this one, this Jz is equal to Lz plus Sz. Okay, so that this Lz will be equal to Jz minus Sz. So using that substitution, this Lz is equal to Jz minus Sz, this will be obtained like this: GL into Jz, then plus, really there is this minus GL into minus this Sz. Okay, that goes to this part. So this Gs minus GL into Sz into mu n divided by H cross. Now taking the expectation value of this system or this equation, when Jz is equal to Jh cross, the result will be like this. Okay, the expectation value of mu will be equal to this one, GL into J, means the Jz component of the expectation value of this Jz will be the Z component of J, that is this J will be the result, J into H cross will be the result. So this J into the H cross is outside is the outside, then this j into then the expectation value of gs minus gl in the expectation value. So since this is a constant, this expectation value of sz, then this h cross and this h cross get cancelled, then this h cross remains only this the third term, that is gs minus gl term. Okay, so this becomes this one. Now again we have to calculate what is the expectation value of sz. So we utilize another trick. So to calculate the expectation value of sz, we know that the sz is varying, the sz component is the magnitude of sz component is varying continually, but we know that the sj component we can also split like this lj plus sj produce this j. So this the component of s along this j remains a constant at any time, so that the expectation value of sz will be equal to expectation value of sj, and which can be obtained like this. So this is from this one we can write this sj using this one, means sj means the component of s along the j. So this can be written like this, s dot j divided by the magnitude of j. Now taking this 1j, one upper side and lower side, this becomes j into s dot j divided by j square, so that this s and this s dot j is calculated from this one s dot l plus s, where this s dot l plus s square. Now this s dot l can be replaced from this one. We can the squaring this j is equal to l plus s equation, we will get j square is equal to l square plus 2l dot s plus s square, so that l dot s will be 1 by 2 into j square minus l square minus s square. So substituting here this l dot s or s dot l, substituting here and plus s square, we get this one 1 by 2 into j square minus l square plus s square. Okay, so now the expectation value of this one means here we substitute this one, that is expectation value of this s dot j or this expectation value of j into expectation value of s dot j divided by expectation value of j square. So all these are substituted to get the expectation value of sj. So the expectation value of j is again jz means jh cross, so the j itself. Then the expectation value of s dot j is calculated from this equation, and expectation value of j square is, we know that it is j into j plus 1 h cross. So substituting all these here, we will get like this. Okay, so j by the expectation value of this j is this j, and the expectation value of this s dot j is this equation, the expectation value of these ones, that is 1 by 2 into j plus 1 minus l into l plus 1 minus plus s into s plus 1 into h cross, then divided by the expectation value of this j square is again j into j plus. So this we get this one. Okay, now we substitute this expectation value of sz here, xz here, and for different j values, for this j can be l plus half and l minus half. Since s can be plus half and minus half, the spin values may be plus half and minus half, so that this j can be l plus half and l minus half. So this is when j is equal to l plus experimental value, substituting in this equation. After substituting, you can see experimental values of the magnetic moment. This mu is of odd neutron, odd proton plus gs by 2 shell model. So similarly for j is equal to L minus experimental values, this is obtained. Okay. So this corresponds to j is equal to L minus half, and this corresponds to j is equal to L plus half. And the Schmidt lines are the solid, means these solid lines represents the predicted the mu values or predicted magnetic moments in terms of mu n, in terms of nuclear magneton. These are the predicted magnetic moments. You can see these solid lines, the solid line on the upper part and lower part, they corresponds to, the solid line corresponds to with gs equal to gs itself, means the gs is not modified. This is for free nucleons, free particles, the gs is 2, but it is somewhat modified. But for the, when the gs is modified by this, is 0.6 times the original free particle gs, these dashed lines are the predicted values using the above discussed equations. So these lines, means these predicted lines of the this nuclear magneton, these magnetic moments, are called Schmidt lines. Schmidt lines. Okay, so these are the Schmidt lines. Okay, so you can see these Schmidt lines almost nearly, even though it is not exact, it is displaced by some orders, it is almost matches with the experimental values, and there are some errors with some particular cases, the great errors, the large error with some particular cases. This almost are in align with the prediction of the shell model. Okay. Now the fourth prediction is electric quadrupole moment. We know that the electric quadrupole moments are generated by the 4 charges like this, and for the case of nucleus, the electric quadrupole moment is calculated by evaluating the electric quadrupole moment operator, that is 3z square minus r square. So that this is multiplied by again the charge E. So this is the electric quadrupole moment, E into the psi star 3z square minus r square psi d v, the volume integral. Okay. Now if the angular momentum is aligned with z axis, means if the angular momentum direction is z axis, that means the nucleons are orbiting mostly in xy plane, since the angular momentum direction will be normal to this spinning direction, the precession direction. So that is why this is said the nucleons are orbiting mostly in xy plane, and the result in a negative quadrupole moment, because since most of the nucleons are in xy plane, this z will be very small or negligible, so that this is neglected, so the remaining will be this r square term, so that is why the electric quadrupole is almost equivalent to the expectation value or average value of this negative of this r square, and the direction is a negative quantity. A more refined quantum mechanical calculation gives the single particle quadrupole moment of odd proton in shell model state J. Okay, means if the finally filled proton momentum or the spin is J, then this electric quadrupole moment, single particle, this electric quadrupole moment equation is this one. This is more corrected from this one, this above classical one, that is 2j minus 1 divided by 2 into j plus 1 r square. Again the negative sign is there, where for the uniformly charged sphere charged sphere case, spherical case, this r square will be 3 by 5 r square, where this r is the radius of the nucleus, which can be replaced by this equation. There is, you know that the radius can be represented by r0 a raised to 1 by 3. So this will be the result. Okay, so in short, we can calculate by the approximate calculation. We can calculate the electric quadrupole moment using this one, and a more refined value using this one. So these are the predicted values and experimental values for different shell state. For this one and for this one, you can see these calculated values are this one all are negative, but you can see for the case of proton, means the single finally filled odd proton, the experimentally calculated values are this one. You can notice the difference between the two. Generally, these experimentally obtained values are 2-3 factor greater than these calculated values, or the calculated values are 2-3 factors smaller than these experimental values. Okay, so this is a general observation, but this sign is perfectly matching. These all are negative, these all are again negative. Even though this is differential, this is differed by the 2-3 orders, 2-3 times, but almost matches. Within that limit, they matches. Okay. Similarly, for the case of neutron also, the finally filled odd neutron case also, you can see there is the these values. There is the experimentally obtained electric quadrupole moment values are there. So these are the values. Even though this is much less than this protonic electric quadrupole moment values, this is 0.12, this is 0.02, this is 0.08, this is 0.06. So this is always less than this protonic case. Classically, we expect a zero value. Okay, but there is a value. There is an electrical quadrupole moment value even for this neutron. We know that the neutron is a neutral particle, but if we take the shell model, the single particle shell model, means the finally filled odd neutron produces, or the nucleon produces all the properties of the nucleus. In that case, this is some error, because in that case this cannot produce this one. Okay. So when the final subshell contains more than one particle, we already know all that particle can neutrons are not a fundamental refinement. Another refinement, there is more fundamentally fundamental. So the corresponding quadrupole fundamentally smaller in terms of the single particle quadrupole moment. This will be the single particle quadrupole moment into 1 minus 2 times minus 1 by 2j minus 1, where this j is the finally filled spin state and this n is the number of nucleons in the final subshell, that finally filled subshell. Okay, where this n can be from 1 to 2j, since this can accommodate 2j plus 1. The 2j plus 1 case corresponds to a 0 case, 0 electric quadrupole moment case. So this can be up to a maximum of 1 to 2j. Okay. So when n equal to 1, this is again a single particle model. So again when n equal to 2j, there is a hole, means there is an absence of a single nucleon in that orbit. So again substituting n equal to 2j, we get this q is equal to minus qsp, and we take this one as the q of hole, or the electric quadrupole moment of a whole nucleus. Okay. So now these are the complete experimental values of the both neutronic and protonic and also the Hall cases. Means the absence of a single proton in the final orbit and absence of a single neutron in the final orbit in that case also. And we also found that the Hall case is just differed by a negative sign. That means in their case the electric quadrupole moment will be positive if this is negative. If the single particle case is negative, the single Hall case will be positive one. So these are again the calculated values, and these are the single particle model, and these are the single Hall model. Okay. So the sign matches, even though the sign matches, their magnitudes are much differ from the calculated values or predicted values. Okay.